All right, in this chapter 7.4, or this subchapter I should say, I'm going to be covering the basics of empirical formulas, molecular formulas, and how to calculate both of them using just some given information. Now, this chapter can be a little bit confusing if you didn't do chapter 7.3, which talks about a lot about how to calculate the molecular numbers and molecular mass, those sort of stuff. But if you have all that covered, it should be pretty easy. So the first thing you need to know is the empirical formula. So empirical formulas, they're pretty similar to molecular formulas. They just show the relationship of number of atoms in a compound. So for example, let's see diborane. Diborane is a compound, and its empirical formula would be BH3. Boron, hydrogen 3. The only difference between molecular and empirical formulas is that empirical formulas don't show the exact number of atoms of each element. So although it says BH3, it doesn't mean there's one boron atom and 3 hydrogen atoms. In reality, there's actually 2 boron atoms and 6 hydrogen atoms. The only reason we write it like this is because we simplify it to the nearest whole number ratio. And that's all empirical formulas do. They just simplify the smallest whole number ratio. Because you see here, the ratio to number of B atoms to hydrogen is 2 to the 6, which is just 1 to 3. In this case, it goes here, 1, 2, 3. 1, 3. Now next, you all know this already, but molecular formulas just show the relationship between the number of atoms in a compound. Molecular formula. Now, there are some instances where the molecular formula and the empirical formula can be the same. So let's look at H2O, which is just water, right? The empirical and molecular formula are exactly the same because the ratio to hydrogen atoms to oxygen atoms is just 2 to 1. That's as small as it gets. It can't be any smaller than this. So this would be both the molecular and the empirical formula. So just to quickly overview what we've done so far. BH3. This is the empirical formula. Right? It shows the simplest whole number ratio between 2 different elements. Or it doesn't even have to be 2, but in this case it is 2. And the actual formula would be B2H6. This is the molecular formula. And there are some cases, like I just mentioned, where the empirical and the molecular can be the same. So just like this one, because this is the smallest ratio, 2 to 1, this is as simple as it gets. Alright, so those are the basics about empirical formulas and molecular formulas, which just show the number of atoms in a compound. Next, we're going to be trying to calculate the empirical formulas of a compound by using only the percentages of each atom in that compound given. So that didn't really make a lot of sense when I said it, but when I write it out, it'll make a lot more sense. So here's an example question. Question 1. Let's say the information given is that we have a compound, and that compound is 78.1% B boron and 21.9% H hydrogen. Now, using only this information given, we need to try to find out what the empirical formula of whatever this compound is. Now, there's a series of steps which we need to take, which are pretty simple, that allow us to figure this out. First step is we're going to assume that we have 100 grams of this substance. This just makes it really easy for us to calculate percentages because it's 100 and it'll be a gram, so it'll be really easy to work with. So let's say we have 100 grams. Of those 100 grams, what percent of them is boron? B, 78.1%. So that just means we're just going to have 78.1 grams of boron out of the 100. right? Same goes for hydrogen. We'll have 21.9 grams of hydrogen out of that 100. So that's the first step, pretty easy. We just find how many grams of each substance we have. Second step is we're going to have to calculate the number of moles. Now, we went over this in 7.3, but I'm just going to assume that you know all this information. So the mole, the way we do this is we look at the periodic table, and we can look at the atomic mass unit of our atoms. This gives us the number of grams there are in a single mole of the atom. So on the periodic table, if you look at boron has an AMU of 10.811. We'll just say like 10.8. Hydrogen has about 1. Exactly, it is 1.007, but we'll just say 1 for simplicity's sake. Now, using this, we can find the exact number of moles in this compound. How do we do this? Well, we just divide the number of grams by the AMU, because the AMU is just grams per mole, right? So 78.1 divided by 10.8 equals 7.22. So this just means we have 7.22 moles of boron. Pretty simple, right? If we do the exact same process for hydrogen, then we'll get a pretty similar thing. Hydrogen, 21.9 grams divided by, what is it, this? 1.000 something. You get about 21, right? 21.7 to be exact. So that's the second step done. We just found the number of moles and the number of moles for each atom in this compound. So if I write this on the bottom here, we have 7.2, I'll just simplify a bit, B, 2, 21.7, H. This is the second step done. Now third step, we just need to, and this is the final step, we just need to divide these two numbers by the element that has the smallest, I guess, number. So in this case, it'll be boron because it's 7.2. It's not 21.7. 7.2 is a smaller number. This way, we just divide each number by 7.2, 7.2. This will give us B equals 1, or just 1B, to about 3H. And it's not going to be exact all the time, but you will get pretty close to a whole number. Now, this is basically our answer for the empirical formula. For the empirical formula, we'll just write B1, H3. This just means in the empirical formula, you would write it as B1 boron atom and 3 hydrogen atoms. Now keep in mind, this isn't the exact numbers of atoms in the compound. In reality, diborane, which is BH3, has 2 boron atoms and 6 hydrogen atoms. But we're just writing it like this in the empirical formula because it is the smallest whole number ratio. You just need to keep that in mind. So this is going to be the last thing we cover in this subchapter 7.4. And it's going to be calculating molecular formulas using only empirical formulas and some information given. So let's say, for example, you're given this compound, P2O5. This is the empirical formula of phosphorus pentoxide. And using this and one more thing of information, which is the molar mass of this compound. Using only this information, they ask us to find the molecular formula, which will show the exact number of atoms of each atom in this compound. So, just like the last thing we learned, which was finding empirical formulas, there is a set of, I guess, steps that we can take, which are pretty simple to find the molecular formula. So first step, there's one formula we have to keep in mind, which is X equals molecular mass, which is AMU, over, or divided by, empirical mass. And using this, we can basically find the molecular compound of any compound. So first step, we can just plug in what we know. X we don't know, empirical mass we can find out later, but right now what we do know is the AMU, which is this number right here. The AMU of P2O5 is 283.89 grams per mole over empirical mass. Just write EM for now. Next step, we need to find the empirical mass. Now, although we don't have the exact number given to us right away, it's really easy to calculate the empirical mass. We just look at the empirical formula we were given and multiply each atom by its AMU on the periodic table. So, for example, let's take a look at phosphorus. Phosphorus on the periodic table, if you look at it, P has an AMU of 30.97 something. We'll just say 30.9 for simplicity's sake. Right? Oxygen has an AMU of 15.999, which we'll just say is 16 to keep it easy. Now using this, we're going to multiply, we take these numbers, you see 2 and 5, we're going to multiply each number, each AMU, by the respective number of atoms. So 30 times 2, because P30, P2, we'll do 30.9 times 2, and add that to 16 times 5. 16 times 5. Right? And if we add all this together, we get about 141.995 grams per mole. Now, this is what we call the empirical mass of the empirical formula. So P2O5 has an empirical mass of 141.995 grams per mole. But this is empirical mass. This is the smallest whole number ratio. The actual mass is 283. Keep that in mind. So now, all we need to do is divide these two numbers, the actual mass by the empirical mass. And if we do that, we can do 283.89 divided by this number right here, 141.995. If we do this, we get a number that's roughly equal to about 2. It's not exactly, but it's pretty close. So now what do we know? We know x is equal to 2. That's kind of a long first step. It's actually a series of steps inside that step, but that's how you find x. Now to the second step, we use x to find the actual molecular formula. And this part is really easy. All we do is multiply the empirical formula, which is this, times x. Now we know x is 2, so we can do P2O5 times 2. All we gotta do is multiply this number, each of them, by this number. So in this case we have P4, and then O10. And that's the answer. This is our molecular mass, our molecular formula of phosphorus pentoxide. So this is equal to the molecular formula. So that's all that's really covered in 7.4. It is pretty complicated if you don't know a bit about 7.3, but 7.3 is pretty simple. All you gotta know is how to calculate molar mass, number of moles of an atom, and that sort of stuff. And if you can figure all that out, it's pretty straightforward from there.